class. Yes, limits. Very good. But what is the second thing that we study a lot? Of course, limits and what else? Right. But what is specifically? There is some true, but something else that we work on for different functions. Exactly. So right now in the last two sections of this chapter, we are putting together the limits together with the difference quotient. Did I start that? Yes. With the difference quotient. We are putting these two together. Okay. So let's go back and see what this does and why and what it means, etc., etc. Yes?
This is 2.7.
2.7 and continues with 2.8. Finish? Yeah. Thank you. Very good. So, back to our favorite drawing. Here it is, our favorite drawing, f of x. Okay, please remind us what p is and what q is. What are the coordinates of p? P has coordinates very good. And this is very good. And this is x plus h. And this is f of x plus h. So the coordinates of p and q are x, f of x, and q, x plus h, f of x plus h. Good. So now can anyone give us the average rate of change between p and q? Average rate of change between p and q, which is also the slope of the secant line pq. Can anyone give us that? And name it, please. Nothing new. Difference quotient, very good. This is indeed the difference quotient. Can anyone dictate the difference quotient? Very good. Very good. We've done this for many functions. Perfect. And now here is what we've done before many times. I want the slope of this line. What is this line called? It's not the secant line, PQ, but this line is the tangent line at P. This is the tangent line at P. So can anyone tell us how to find the tangent, the slope of the tangent line, the slope of tangent line at P, x, f of x. I'm going to erase that. So please tell me how to find the slope of the tangent line at P. As h approaches 0. The slope of the tangent at P is the limit as h approaches 0 from f of x plus h minus f of x divided by h. Let's stop. This is extremely important. We've done this a lot, but we did not put these two concepts together. This is the first time we see these two concepts together, the concept of the difference quotient and the concept of the limit. Do we understand this? So as h gets closer and closer to 0, the secant line gets closer and closer to the tangent line. Therefore, the slope of the secant line gets closer and closer to the slope of the tangent line. We no longer write closer and closer because we have this limit operator. This is what this means. As h gets closer and closer to 0, the limit of the difference quotient will give us the slope of the tangent line at P. Any questions? Since, yes, please.
What is that, the first?
The slope of the tangent at P. My apologies, because I stand and I write, my handwriting is not perfect. It's not perfect, period, in general, but especially now. I'm sorry about that. Good. So this has a name. Since P is a generic point, x comma f of x, any x comma f of x, this has a name. Anyone remembers or knows the name of this? You don't have to. Yes. Thank you. The derivative. And since it's x and not a, is the derivative function that gives the slope of the tangent line at any point P. There is a restriction, though. I'm going to put in parentheses, where the derivative exists. I'm going to talk about that in a minute. Where the derivative exists. The derivative will not exist at every point. So let's go back. So what does this mean? This is just the name. And what is the notation? The notation is f prime of x. So you either say f prime of x, or you read the derivative function of f of x. So we prefer f prime of x. So what does this give? At any point P, anywhere you want. P can be here, or it can be here, or it can be here, or it can be here. It doesn't matter. At this point for this x, at this point for this x, at this point for this x, and so on and so forth, this function will give us the slope of the tangent line at any point. What else will it give us? The rate of change. Awesome. I will say, or the rate of, I would say the instantaneous. Instantaneous. The instantaneous rate of change at any point P with the same restriction where the derivative exists. Let me read it one more time. It's the derivative function that gives the slope of the tangent line at any point P where the derivative exists, or it gives the instantaneous rate of change at any point P with the same restriction where the derivative exists. So there is only one definition of the derivative function. One definition of the derivative function. Let's write it one more time. F prime of x is the limit as h approaches 0 from f of x plus h minus f of x divided by h. This is the derivative function. The derivative function that gives the rate of change, the instantaneous rate of change of any function that has a derivative at that point. Before we pick some functions to determine their derivative function, before we do that, we'll do it with specific functions first and then any function you want. I would like to go back for a moment and explain when a function does not have a derivative. We say the function is not differentiable. When a function is not differentiable. One more time, what does that mean? When a function is not differentiable. In parentheses, when its derivative does not exist. When its derivative function does not exist. There are a few situations that we have to be aware of. when its derivative function does not exist. I'll go back. So when a function is not differentiable, in other words, when its derivative function will not exist, few situations. Here's a situation, and you will tell me in general. I can give several examples. I claim that at x equals 1, this function is not differentiable. Its derivative at that point does not exist. Why? So here's why. Remember, what is the derivative? It gives the slope of the tangent. But if there are two tangents, which one is it? And right here at this point, here's one tangent, and here's another. So at this point, where the function is not continuous, the function is not differentiable. So at any point where a function is not continuous, the function is not differentiable. So not continuous is a situation in which a function is not differentiable at that point. Two tangents, not acceptable. Okay, here's another situation in which a function is not differentiable. At this point, I'm going to say again 1. Why is this function not differentiable here? And this is called a corner. If a function has a corner, it's not differentiable at that point. Why? Because it has two tangents. One is here and one is here. Not possible. When a function, even if it's continuous, if it has a corner, a function is not differentiable at that point. Another very similar situation is like a cusp. Imagine between two teeth. Something like this. Cusp. A cusp, not differentiable. Two tangents, one here and one here. Which one is it? What does that mean? So let's come back here for 1 second. When does this limit exist? When h approaches 0 from either side. If the limit from the left of 0 and the limit from the right of 0 are the same. But the limit from the left will give us one tangent, and the limit from the right will give us another tangent. So the limit from either side will not exist. And that's the situation here and here. As h approaches 0 from this side, we get a negative number. As h approaches 0 from this side, we get a positive number. So the limit from h approaches 0 for h approaches 0 from either side does not exist. So if the function is not continuous, if the function has a corner, even if it's continuous, or a cusp, the function is not differentiable. And there is one more. Last one is vertical tangent. Here's a situation in which a function has a vertical tangent. The limit from the left of 0 will be infinity, and the left from the right of 0 will be whatever, and it does not exist. So in these 4 situations, the function is not differentiable. Okay. So there are several super important functions for which I would like us to, just determine the derivatives by hand. Ready? Here's one very important function, and once we finish determining its derivative, moving forward, we have to remember it. So we are asked to find the derivative of f prime, the derivative of the square root of x. How do I start? What is the definition? We can never forget this definition. What is it? What do I have to write? Limit. Very good. Awesome. From? You're right. I should have written that definition first. Good. So we are determining now a function that will give us the rate of change, the instantaneous rate of change of this function at any point where this function is differentiable, where its derivative exists. We know how to handle this. We've done this before. I never told you what it was, but now you know what it is. So, first step, I plug it in. What do I get? I hope 0 over 0. It is 0 over 0. Good. And what will you do? How do we handle this function always? Excellent. So we multiply and divide by the conjugate. Can anyone give us the conjugate? Excellent. Well done. That's what I want to hear. Good. So then this is limit as age approaches 0. I will write the bottom because I'm lazy. And I'll wait for you to give me the top. Because you are experts now. Good. So now let's stop for a moment. I'm determining the difference quotient. Two things must happen. That don't have h must go away. The second one is the h from the denominator has to go away. Excellent. Well done. Thank you. Good. So these two go away as expected. Then limit as age approaches 0. Age at the top, age the square root of x plus age plus the square root of x. At this point, I get rid of this. I remember the second step has to happen. At this point, I can eliminate the limit operator. I can drop the limit operator and find the answer. So please tell me the final answer. A function that will give the rate of change, the instantaneous rate of change of the square root of x at any point where the square root of x is differentiable, where it does not have a cusp, a corner, or a vertical tangent, or it's undefined, which means not continuous. What is the answer? Bless you. 1 over? Which is 2 apples? Good. 2 the square root of x. This is it. So when age approaches 0, you have the square root of x plus the square root of x. An apple plus an apple is 2 apples to the square root of x. So now let's look at this function. Yes, Ricky?
What happens to the h under the black?
Age approaches 0.
Okay.
So look at this function and say, the original function is defined at the point, but this one at that point is not, which means the square root of x is not differentiable at that point. Which value of x? The function exists, but its derivative does not. Which point? 0. X equals 0. F of x, which is the square root of x, is not differentiable. The denominator cannot be 0. So the square root of x prime is 1 over 2 the square root of x. Moving forward, this has to be committed to memory. We will not talk about it again. I'm kidding. If you need me to prove it again, I will. But I'm hoping that moving forward, we don't have to talk about it again, and we will remember it forever. Any questions on this? Any questions? Yes, please.
So if it wasn't as h approaches 0,
But that's the definition of the derivative. There is only one definition. When age approaches 0. I can change that. Very good. Okay, so let's pick some problems from page 163.
Ricky has a question.
Oh, yes. Sorry, Ricky.
So it's not
Differentiable. Yes. Yes.
because
The function is defined as 0. The square root of 0 is 0, but its derivative is not. So the function is not differentiable when the derivative does not exist. And that is at x equals 0. From all the domain, it's the only, so the domain of this function, can anyone refresh our memory? Maybe I should add this function to the list of functions because this is so important. Can anyone give us the domain of the function? Of course, 0 to infinity. So the function is defined on 0 to infinity, but its derivative is not defined on 0 to infinity. It's defined everywhere on 0 to infinity, but not at 0. Okay, good. So the derivative from the right of 0, as h approaches 0 from the right, at 0 will not exist. Will be infinity or dne. Will be infinity. Right? Okay, very good. So I would like to pick another function, x squared, before we continue. So let's say f of x equals x squared. We would like to determine the function that gives us the rate of change, the instantaneous rate of change of this function at any point where the function is differentiable. So what do I have to write? Yes, so for this function we have f prime. Ricky, any questions? Yes, Ricky, go ahead. Okay, I was right. I was asking you that. F of x plus h, let's write it because Emily's right. I should write the definition first before I plug it in. So limit as h approaches 0. F of x plus h, and very good, minus, perfect, excellent, divided by h. Good. We have two options. One option here would be to use the difference of squares, if you like, or expand. You tell me what you want to do. You want to use the difference of squares. Perfect decision. I commend you for that. Perfect. Well done. Good. So, say it again. Yes, please. More? Perfect. Good. Very good. Do you all agree with x plus h plus x and x plus h minus x? It's a squared minus b squared, a plus b, a minus b. Right? Good. So obviously these two go away. So then limit as h approaches 0, 2x plus h times h over h. So what would happen next? We will cancel out. Very good. Please drop the limit operator and give us the function that will always give us the derivative or the rate of change, the instantaneous rate of change of f of x, or the slope of the tangent line at any point on f of x. So from now on, we will remember this. Now, question for you. What can you say about x? Yes, please. Chris? Right. We haven't gotten to that yet. Yes. The exponential rules come in chapter 3. But yes. Correct. Yes, Vanessa?
Where does that h go? In the parentheses?
Well, we know limits,
Oh,
right?
okay.
We know limits. When h approaches 0, that's when we drop the operator. And h approaches 0, and the answer is 2x. Are you with me, everyone? Mm-hmm. Yes? Perfect. So now I'm asking you, where is this x squared not differentiable? It's always differentiable. Look at 2x. So what do we conclude? And we can say the conclusion is about any polynomial function. What would you say? Always differentiable. Always differentiable. And then I have a question for you. So theorem. All poly functions are differentiable on negative infinity to infinity, all real numbers, on all their domain. They're always differentiable, everywhere, on all their domain. Any questions? Any questions here? Yes, Ricky?
So if it wasn't differentiable, then 2x would be in the denominator.
It depends on the function. It's a very good question. Right? It depends on the function. I can't give a recipe. Again, I have to look at the function. But yes, if there is something in the denominator and the function is defined there, but the derivative is undefined at 5, and the function is defined at 5, I would say the function is not differentiable at 5. Its derivative doesn't exist. Yes, Vanessa?
I know I answered my own question. I was just asking if the final answer is.
So all polynomial functions are differentiable everywhere, on all their numbers. Any questions? Anything else? Okay, what if we have a function like, let's say, on page 163, I would like you to pick page 163. Then I would like to look at a word problem with you. Okay, can we pick a function from 163 between 21 and 31?
Can we do 24?
We want to look at 24. It's just that it's quadratic and it has 1.5 in front. It's not. It's going the same thing with x squared. It's not going to be a big deal. So I'm looking at, let's say, maybe a 28, which is a rational function. We've worked with this before many times. Or if you like, maybe x to 3 halves. But maybe a rational function to refresh our memory on how to handle that, if you want. If not, I'm fine. Like, we can do something else. We really don't need to pick another function.
We do those two.
Which one?
The rational function.
The- Yeah, let's look at the rational function. There is no secret there whatsoever. We've done this before. It's just a long process over 2x minus 3. Okay, so we want to find f prime for this function. It's going to be a long process, especially because of x squared at the top. So limit as h approaches 0, f of x plus h minus f of x divided by h. So this is limit h approaches 0. Yes, it's a long thing. So if we have x plus h everything squared minus 1 over 2x plus 2h minus 3 minus x squared minus 1 over 2x minus 3. So we have to replace x by x plus h, and I did it at the top, and I did it at the denominator, and then this is f of x. As the next step, we have to find what? Of course, the least common denominator. It's going to be a long thing. You know I'm going to run out of space. I always do. So get on board with that. So I will simplify this before I use the adjustment of 2x minus 3 and the adjustment of 2x plus 2h minus 3. But I'm going to simplify it first, right? So we do have, let's write it so everyone sees what we're doing. I don't want to skip steps, so let's write it. So I'm going to write 2x minus 3, but do not simplify with the denominator, please. So this is x squared plus 2xh plus h squared and minus 1. And then minus x squared minus 1 and 2x plus 2h minus 3. So I didn't do anything. I did not multiply yet. I only found the least common denominator, both factors. And I wrote 2x minus 3, and then I only expanded x plus h squared, and then, of course, minus 1. I wrote x squared minus 1, and I copied to x plus 2h minus 3. I did not multiply yet, because I was going to run out of room anyway. Is this clear? Yes, everyone? Yes.
Where
Yes.
does the middle part come from, the x squared plus 2xh plus h squared minus 1?
Okay. It's a very good question. Can anyone answer where we get x squared, x plus h everything squared? Three terms, right? That's the first handout we looked at.
So you're factoring.
No, I'm expanding. X plus h squared is this, and then minus 1. And all these terms have to be multiplied by 2x minus 3.
Would it be x plus h, or x plus h plus 1, and then x plus h plus 1?
No, because you're replacing x, not in 1. So you are replacing in here, not in here. You're replacing x by x plus h. You can't incorporate -1 in it. So this is x plus h, not this. Is that clear?
Yeah. Because on the last problem, when we expanded the same thing, we had x plus h plus x and x plus h minus x.
We use the difference of squares. We're not factoring this. We're distributing. We're distributing to x minus 3 to this quantity. We're not using the difference of squares. Because then we're going to have 3 factors. 2x minus 3 and then a minus b plus and a plus b. We need to multiply this by all this.
Yeah.
I don't need it factored. I need it expanded so I can distribute. In the previous example, I know exactly what you're referring to. In the previous example, we could have written x squared plus 2xh plus h squared and minus x squared. We just decided to factor. But we could have written x squared plus 2xh plus h squared minus x squared, and we would have gotten the same thing. By factoring h, and we would have gotten this.
So that's the same thing as factoring where it's x plus h plus x, x plus h.
Yes, because this is a and this is b. A squared minus b squared, a plus b, a minus b. So we factored because we wanted to do that. But we didn't have to. We could have expanded. But here I have no choice. Because if I factor here, I will never be able to distribute. I will have 3 factors. And then I have to go back and multiply them. So ready? So as I said, this is a long process with this particular function. So I'm going to just flip. So h, 2x minus 3, 2x plus 2h minus 3. And now I'm trying to multiply all these, and hopefully all terms with without h go. Yes, it's a long one because of the x squared. Yeah, because of the x squared. So 2x times, so this is 2x cubed plus 4x squared h plus 2x h squared minus 2x. And then minus 3x squared minus 6xh minus, and I'm going to continue at the top, I don't have room, minus 3h squared and plus 3. So this is only this product. Minus 2x cubed minus 2x squared h, and then plus 3x squared. And minus plus 2x plus 2h minus 3. So I'm checking 2x cubed plus 4x squared h plus 2x h squared minus 2x. And then plus minus 3x squared minus 6xh minus 3h squared and plus 3. Yes. And then x cubed, 2x cubed plus 2x squared h, but with minus in front. And then positive 3x squared. And then 2x, 2h minus 3. Good. I know. It's just because of that x squared. Yes, please. Dylan?
The last subtraction is just the,
So this continues here and continues here.
is that in parentheses at the top?
No parentheses at all.
So
None.
is it just minus or is it minus?
By writing minus here, it tells you that I am continuing, that it's not minus minus. Only telling you that it's not the end. Yes, quiet gentlemen. So negative 2x squared and negative 2x cubed plus positive 2x cubed. Then we have positive 2x with negative 2x. And then we have 3x squared with negative 3x squared. Then we have positive 3 with negative 3. I'm hoping that more go away, but it doesn't look like it. Okay, this is it. It's a mess. That's okay. After we finish this problem, the headache will go away. So let's see. 4x squared h with this. So limit, stage approaches 0. 2x squared h. Then xh squared is alone. 2xh squared alone. This one, yes, minus 6xh alone as well. Negative 3h squared alone as well. And then plus 2h. No, we don't have to do this again, but it's good to do it once. It's fine. Okay, 1, 2, 3, 4, 5 terms at the top. They better have something in common. Because we don't want to do this again. What do they have to have in common? For sure. Yes, otherwise I can continue, right? So I started with 5 terms. I need 5 terms in parentheses. Ready? 2x squared, yes, plus. Very good. Minus. Excellent. Excellent. Good. Finally, h with h, and now I can drop the limit operator. Which terms go away? Definitely this one, definitely this one, and definitely this one. Why do they go away? Because h approaches 0. And final simplified form is 2x squared minus 6x plus 2, everything divided by 2x minus 3 to the, that's it. Good. Okay. There is nothing else we can do. Absolutely done. Yes. Okay. I would like us to look at problem 48. Any questions? Do we still need time to copy?
Yeah.
Okay. Got it. Got it. Here's a question for you. Continuity, differentiability. Continuity, differentiability. What is the relationship between the two? Does continuity automatically imply differentiability? Does differentiability automatically imply continuity? We've seen functions that are continuous, but they're not differentiable. So this implication is false. If a function is continuous, the function doesn't have to be differentiable. You may have a corner or a cusp or a vertical tangent. But if I say, or we're told that the function is differentiable, is it clearly continuous? Absolutely, it must be. So this way, this is always true. This is false. So if a function is differentiable, it's automatically continuous. If a function is continuous, it does not imply that it's differentiable. Perfect. Okay, here is a word problem that I would like us to analyze. Here it is, 48 on page 152. 48 on 152. Okay, here it is. It's not going to stay. Okay. Of course, it's not going to stay. Good. So let's read it. The number of bacteria after T hours in a controlled lab experiment is n. N is the number. F is a function of time t. What is the meaning of the derivative f prime of 5? What are its units? T is in hours, n is the number, f of t is number, t is hours. What does f prime of 5 represent? Yes, please, sure, go ahead. Oh, I'm sorry, 152. Thank you. So immediately after 5 hours, f prime of 5 gives the instantaneous rate of change of the number of bacteria with respect to time. And the measurement unit will be, remember, it's a rate of change. It must have a measurement unit coming from the top over a measurement unit coming from the bottom. Exactly. So f prime of 5, we're going to write it together. Please write it down, and I'll write it after we finish. So f prime of 5 represents immediately after 5 hours. That's what it means. Immediately after 5 hours, f prime of 5 gives the instantaneous rate of change of the number of bacteria, bless you, with respect to time. One more time. Immediately after 5 hours, f prime of 5 gives the instantaneous rate of change of number of bacteria with respect to time. And the units are number of bacteria per hour. Number of bacteria per hour. Part B. Suppose there is an unlimited amount of space and nutrients for the bacteria. Unlimited. Which do you think is larger? F prime of 5 or F prime of 10? If the supply of nutrients is limited, would that affect your conclusion? So let's think about this. So if there is unlimited space and nutrients, right, the bacteria grows and grows faster and faster and faster and faster. Yes. Right? So f prime of 10 will be a higher rate because it multiplies, right? It'll be a higher rate than f prime of 5. But what if this is just this room? They only have this room. So we have 24 people in here. I can bring 24 more. I can bring another 24, another 24, but at some point in time, the rate of change will slow down. At the very beginning, 5 hours, high. But at 10 hours, I can fit. I can bring another one, maybe another one, but the rate of change is slower and slower, correct? So I will write this. Unlimited resources, f prime of 5 is larger. Unlimited resources, f prime of 5 is larger. With limited resources, f prime of 10 is larger. I know I only have 1 minute, so let me write it down. So this was 48 on 152. So f prime of 5. Did we write what this is? Or do I still have to write it in words what f prime of 5 means, or did you all write it? We did? Okay. So unlimited space, nutrients, and so on and so forth. F prime of 5 smaller than f prime of 10. Limited resources, etc. F prime of 5 larger than f prime of 10.